There are some problems that seem like you can't solve them because they just start throwing around the mean and the deviation and then start asking random questions. You don't really know how to convert, how far away things are from the mean into a percentage chance, except for the empirical rules for normally distributed data. If you see normally distributed, then right? That means you're talking about means and standard deviations as your center and spread. And when you've got that scenario, you always know these three facts. You always know that 68% of the data is within one standard deviation, 95% within two, and 99.7% within three. You have to memorize those three numbers to go along with those three amounts of standard deviations. It's all coded up in a picture. Um, I guess what I mean by that is you can see it in a nicely drawn bell curve. Um, you can see it even in a not nicely drawn bell curve, and that's about what mine's going to be, right? That's not totally bell curve-ish, but it's close enough, right? We know the mean is going to be here in the middle here, right? And then all we have to do really is just remind ourselves, okay, here's one standard deviation away. Here's two standard deviations away. Here's three standard deviations away. And in the negative direction also. And regardless of what my drawing looks like, if the data is normally distributed, then we know for sure, right, that 68% of the data is here. I'll try to control my comments with some colors. So we'll just do just slightly lighter gray, but I'll make it really thick, right? That's your 68% between these two. So this interior shaded over here, that's 68%. And of course, the actual real world is always messy, but what we're doing is modeling it with normal distribution when it's something that does seem to be usually a bell-shaped thing in the real world. Most things are. Not everything, but most things. Right, so, perfectly balanced, so we get 34% there and 34% there. And if you're paying attention, right, then oh, I know a lot more too, because remember, this is the middle, so that's half and half. There's 50% to the right, so that means that this, everything higher is 16%. So if somebody just asks you, hey, how much of the population is more than one standard deviation above the mean, the answer is 16%. Doesn't matter what the population is and what you're measuring. If it's normally distributed, there it goes. The classic example IQ. 100 is the mean, 15 is the standard deviation. So you go, okay, one standard deviation above 15, above 100, 15 above 100, 115. Oh, 16% of the population has an IQ of 115 or higher, or whatever it might be, right? It might be the average WGU student sleeps 5.5 hours a night, and the standard deviation is an hour. So ask it the other way, right? How long do the top 16% of sleepers sleep? Sleepers that are WGU students sleep in hours, right? I said it to, we're making up numbers here. 5.5 is the mean, right? And I said that the standard deviation is 1, right? And that's all we need. We just need 1 because it asked top 16%, right? If you're asked top 16%, well, that's the half, the upper half above the 68, right? 68 leaves 32, 16 up, 16 down. All right, so the answer here from the made up data would be 6.5 hours. So when it doesn't feel like they gave you enough data, they just said mean this, deviation that. Hey, what portion of them are between this and that? Then you know you've got an empirical rules. Then you know you've got to pull out your 68, 95, 99.7. I'll continue, right? We want to know about uh, the next layer, right? That's the 95%. The 95%, it's quite common. The reason is in social sciences and education, usually our statistical tests are based on the 95%, meaning something has to be the outside 5% for us to go, you know, something remarkable is going on here. This new curriculum is either remarkably good or remarkably bad. If you're still inside this broad range here that covers 95% of the data, right? Then you're kind of considered, oh, no big deal. But because 95% is so important, let me try to get everything highlighted here, and I'll make it thick and I'll make it red so you can really see. The 95 does show up. If you're a student going on to Stats 2, then you'll be seeing this 95% a lot. All right, and a nice hot red. Okay, 95%. And again, right, we can go, oh, that means there's 5% to share on both sides. So that means in this direction, above it is 2.5, right? And below it is 2.5, right? I'm not going to do too much of repetition of the 16, the 2.5, right? It's all in the symmetry. But don't forget, some questions are lower than questions, not higher than questions. And you can even do some work here if you know there's 2.5 above 95, 2 deviations. But there's 16% above 1 deviation, then you can do a little subtraction and figure out that there's 13.5% right in here, right? Just like the 34% over here makes the 68. To get to 95, you have to add 27 to 68, 13.5 on both sides. So again, the question will just differ. Given blah, 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 hours of sleep by this group and the deviation of whatever, how many of them get between blah and blah? Well, I'm saying these random numbers because all it is a matter of counting and standard deviations. And then maybe when we do the computations converted into standard deviations, maybe they were asking how many people get from 1 below to 2 above, right? That's not one of your memorized numbers. But of course, you can go, oh, 1 below to 1 above, that's 68. And then you can do a little work, 16.5 minus the 2.5, there's 13.5. So the answer would be the 68% in the middle one plus the 13.5%. So there might be a little bit of extra work, but it all comes from the memorized numbers, the empirical rules, the empirical numbers. So always convert what they're asking you back into standard deviations. And the 99.7, same deal. Something far away is, allowed to be asked about, and that's 3 full standard deviations. That's 99.7%. So if you want to do the arithmetic there, you'll find that there's only a tiny little sliver of data, 3%, above 3%. Sorry, above 3 standard deviations above the mean. So if you've got anything that's 3 standard deviations away, whether up or down, it's very rare. I mean, in terms of odds or ratios, that's something like 1 in 700. So right? If you're 3 standard deviations above the normal population's ability in math, you're 1 in 700 people. You'd have to have a group of 700 people before you might, have even odds of seeing somebody your skill. So 3 standard deviations, some books don't even deal with it. They just say 3 standard deviations, just say nearly all. 1 out of 700, even when you add them together, it's like 1 out of 350. It's, barely worth mentioning. So some books just go nearly all. I'm not going to boldface it or mark it up or anything like that, but do be ready to deal with it in case you get a question like it for the exam. Just memorize it and then do the same splitting up things, right? 2.5 here, 0.15 there. You could actually figure out 2.35% here. And you might need to if they give you some kind of lopsided question, or like, how many people have an IQ between 130 and 145 given a mean of 100 and a deviation of 15? Did you hear that? 130, 145, deviation 15, mean 100. The 30 and the 45 are 2 and 3 times a standard deviation uh, above the 100 middle. So it looks like crazy numbers, but when you think about it in terms of number of standard deviations, suddenly you can use the empirical rules to figure out an answer. And that's the bottom line interesting thing. Whatever the data is in real world units, just convert it to deviations to get an answer. And vice versa. Once in a while, they'll ask you like the 16% or the 95%, and you'll have to go, oh, that's 2. 95% is 2 above and below. Oh, let me convert that back. 5.5 hours for the mean, 1 hour for standard deviation. I got to take the 5.5 and add and subtract 2 hours, 2 deviations if the deviation is an hour, right? It's just back and forth between the raw numbers, that's the real world data, and the z-score. It's called the z-score. The number of standard deviations is called the z-score. So there you have it.